Where is everything in the universe going? Right now, as you listen to this, you are moving at 1.3 million miles per hour. Not relative to the car on the highway. Not relative to the airplane above your head. Relative to the oldest light in the universe, the cosmic microwave background, the faint afterglow of the Big Bang itself, tells us that you, your couch, your city, your planet, your solar system, your entire galaxy, all of it, is screaming through the cosmos at a speed so absurd that if you could somehow feel it, the wind resistance alone would vaporize you into a thin streak of plasma before your brain had time to register pain. And here is the truly unsettling part. We know we are moving. We can measure it. We can point to the direction in the sky where we are headed. But for decades, we had absolutely no idea why. Something out there, hidden behind the thick dust and starlight of our own galaxy, is pulling us. Something enormous. Something we cannot see. And it may not be the only thing. This is the story of where everything in the universe is going. It is a story that stretches from the neighborhood of our Milky Way all the way out to the largest structures the cosmos has ever produced. It is a story about gravity and its invisible hand, about the strange substance called dark energy that appears to be tearing everything apart, and about recent discoveries that have thrown our best predictions about the fate of the universe into genuine doubt. We will trace the journey of our galaxy as it falls toward its nearest giant neighbor, the Andromeda galaxy. In a collision that may or may not happen billions of years from now, we will follow the invisible rivers of gravity that carry entire superclusters of galaxies toward a mysterious region called the Great Attractor, and then beyond it to something even more massive. And finally, we will look at the end, the final destination, the place where all of this motion, all of this falling, all of this cosmic rushing about will ultimately lead. So settle in. Let the stars wash over you, and let us begin by asking the simplest question that has the most complicated answer. Where exactly are you? Think about it for a moment. If someone asked you for your address, you would give them a street, a city, a state, a country. But those are human constructions, lines drawn on maps by hands that have long since turned to dust. The universe does not care about your zip code. The universe cares about gravity, and in the language of gravity, your address is defined not by politics, but by which gravitational well you happen to be sitting in, which river of cosmic motion you are flowing along, and which massive, invisible concentrations of matter are pulling on you from millions or billions of light years away. Your cosmic address is longer than you might think. You live on Earth. Earth orbits the sun. The sun sits about 26,000 light years from the center of the Milky Way galaxy, nestled in a minor spur of one of the galaxy's spiral arms called the Orion Arm. The Milky Way itself is not alone. It belongs to a small club of galaxies called the Local Group, a collection of about 80 known galaxies spread across roughly 10 million light-years of space. The Local Group, in turn, sits on the outskirts of a much larger congregation called the Virgo supercluster. And the Virgo supercluster is just one lobe of a colossal structure called Laniakea, a supercluster spanning 500 million light-years that contains the mass of roughly 100,000 galaxies. Even Laniakea might be just a subbasin within something even bigger, a structure so vast that we are still working out where its edges are. At every single one of these scales, things are moving. The Earth spins on its axis at about 1,000 miles per hour at the equator. It orbits the Sun at roughly 67,000 miles per hour. The Sun, dragging us, and every other planet along with it, orbits the center of the Milky Way at about 514,000 miles per hour, and the Milky Way itself is barreling through the cosmos relative to the cosmic microwave background at that dizzying 1.3 million miles per hour. Every single one of these motions is governed by gravity. Every single one of these motions has a cause. And to understand where all of it is headed, we have to start at the beginning, with the discovery that the universe is not standing still. The expanding universe, how we learned everything is moving apart. In the early 1900s, most astronomers believed the universe was eternal, unchanging, and made up entirely of the Milky Way. The fuzzy patches of light they saw through their telescopes, objects they called nebulae, were thought to be clouds of gas within our own galaxy. The idea that the universe could be bigger, that it could be changing, that it could have a beginning and an end, these were philosophical questions, not scientific ones. Then Vesto Slipher changed everything. Slipher was a quiet, meticulous astronomer working at the Lowell Observatory in Flagstaff, Arizona. Between 1912 and 1925, he pointed his telescope at dozens of those fuzzy nebulae and carefully measured the light they emitted. He broke their light into spectra, rainbows of color that contain the fingerprints of the elements inside a star or galaxy. And he noticed something peculiar. Almost every single one of these nebulae had spectra that were shifted toward the red end of the spectrum. This redshift, as it is called, meant that almost every nebula was moving away from us. This was baffling. If these nebulae were just clouds of gas inside the Milky Way, why would they all be rushing away? Where were they going? Slipher published his findings, but he did not fully understand what they meant. He could not have known that he was holding the first thread of a discovery that would unravel the entire fabric of our cosmic understanding. The second thread came from a very different kind of mind. Edwin Hubble was tall, athletic, a former boxer, a Rhodes Scholar, and possessed of a supreme confidence that sometimes grated on his colleagues. In the 1920s, working at the Mount Wilson Observatory in California with its powerful 100-inch Hooker telescope, Hubble did something that no one before him had managed. He resolved individual stars within the Andromeda Nebula. Among them, he found a type of star called a Cepheid variable, a pulsating star whose brightness fluctuates in a predictable pattern. The astronomer Henrietta Swan Leavitt had already discovered that the pulsation period of these stars is directly related to their intrinsic brightness. By comparing a Cepheid's true brightness with how bright it appeared, you could calculate its distance. Hubble did the math, and the result was staggering. The Andromeda Nebula was not a cloud of gas inside the Milky Way. It was a separate galaxy, roughly 900,000 light-years away. The number was off by more than half, later revised to about 2.5 million light-years, but the implication was revolutionary. The universe was vastly bigger than anyone had imagined. Those fuzzy nebulae were entire galaxies in their own right, island universes scattered across an unimaginable void. But Hubble was not finished. In 1929, he combined his distance measurements with the redshift data collected by Slipher and his own collaborator, Milton Humason, and he plotted them on a graph, distance on one axis, velocity on the other. The result was a straight line. The farther away a galaxy was, the faster it was receding from us. This was not just motion. This was an expansion. The universe itself was getting bigger. This discovery struck the scientific world like a thunderbolt. Albert Einstein, who had modified his own equations of general relativity with a fudge factor called the cosmological constant to keep the universe from expanding, reportedly called that modification the greatest blunder of his life. When he learned of Hubble's work, Einstein visited Mount Wilson Observatory in 1931 and met Hubble personally. After the visit, Einstein announced that the encounter had changed his mind. The universe was not static. It was alive, growing, and dynamic. The Belgian physicist and Catholic priest, Georges Lemaître, who had independently predicted the expansion from Einstein's equations 2 years before Hubble's observational proof, saw in this discovery the seeds of something even more profound. Lemaître was an unusual figure in the history of science, a man who wore two hats that many of his contemporaries considered incompatible. Ordained as a priest in 1923, he had then studied mathematics and physics at Cambridge, Harvard, and MIT before returning to Belgium to teach at the Catholic University of Leuven. In 1927, working entirely from the mathematics of general relativity, he published a paper in an obscure Belgian journal predicting that the universe was expanding and that the rate of expansion was proportional to distance, the very relationship Hubble would observe 2 years later. For decades, Lemaître received little credit for his theoretical prediction, a historical oversight that has been corrected only in recent years. Today, the relationship between galaxy distance and recession velocity is increasingly called the Hubble-Lemaître law. But Lemaître went further than Hubble ever did. If the universe is expanding now, he reasoned, then it must have been smaller in the past. Run the clock backward far enough, and everything would have been compressed into a single, unimaginably dense point. He called this the primeval atom, or sometimes the cosmic egg. We call it the Big Bang. The name itself was an accident of history. British astronomer Fred Hoyle, who favored a competing model of an eternal, unchanging cosmos, used the term Big Bang dismissively during a 1949 radio interview. He meant it as mockery. The name stuck anyway, becoming one of the most recognizable phrases in all of science. The expansion of the universe is not like an explosion, where debris flies outward from a central point. There is no center. There is no edge. Instead, space itself is stretching, like the surface of a balloon being inflated. If you drew dots on that balloon to represent galaxies, every dot would see every other dot moving away as the balloon expanded. No dot is the center. Every dot thinks it is. This is the nature of cosmic expansion. Galaxies are not flying through space. They are being carried along by the stretching of space between them, and this stretching has been happening since the universe began, 13.8 billion years ago. The implications were staggering, not just for physics, but but for philosophy. For millennia, most human civilizations assumed the universe was eternal and unchanging, a stage upon which the drama of existence played out, but which was itself static. The discovery of expansion shattered that assumption. The universe had a birthday. It had a beginning. And if it had a beginning, it might also have an end. But here is where the story gets more complicated. Because while the universe as a whole is expanding, carrying distant galaxies away from each other at increasing speeds, that expansion is not the only thing happening. On smaller scales, gravity has its own agenda. Gravity does not care about the expansion of the universe. Gravity cares about mass. And wherever mass is concentrated, gravity pulls things together, fighting against the cosmic tide of expansion. This battle between expansion and gravity is the reason the universe looks the way it does. It is the reason you exist. And to understand it, we need to talk about something we cannot see. Dark matter, the invisible hand shaping everything. In 1933, a wild-haired, combative Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a dense ball of over 1,000 galaxies located about 320 million light-years from Earth. Zwicky measured the speeds at which the individual galaxies within the cluster were moving. He then calculated how much mass the cluster would need to keep those galaxies from flying apart, like a gravitational cage holding them in place. The number he got was enormous, roughly 400 times more mass than the visible matter could account for. Something invisible, something he called Dunkelmaterei, dark matter, had to be there. His colleagues dismissed him. Zwicky was brilliant, but also abrasive, known for calling other astronomers spherical bastards, meaning they were bastards no matter which way you looked at them. His claims about dark matter were filed away and largely forgotten. 4 decades later, Vera Rubin proved him right. Rubin was an astronomer at the Carnegie Institution in Washington, D.C., and she had spent years being told, in various ways, that women did not belong in astronomy. When she applied to observe at Palomar Observatory in 1965, she was informed that her time on the mountain would be limited because the building did not have a women's bathroom. A common excuse used at the time to deny women access to telescopes. Princeton's graduate program in astronomy did not accept women until 1975. When she presented her master's thesis at an American Astronomical Society meeting, one advisor told her just 2 things: that the word data is plural, and that her work was sloppy, before graciously volunteering to present it on her behalf because she was pregnant and not a member of the society. Undaunted by any of it, Rubin earned her degrees elsewhere and got to work. In the late 1960s, working with instrument maker Kent Ford at the Carnegie Institution's Department of Terrestrial Magnetism, Rubin began measuring the rotation speeds of stars within spiral galaxies. Ford had designed a revolutionary new image tube spectrograph that could gather spectra 10 times faster than a traditional photographic plate. A leap forward in telescope instrumentation that made their project possible. They started with Andromeda, the Milky Way's nearest large galactic neighbor. Rubin would later describe their observing routine at Kitt Peak and Lowell observatories. While waiting for the photographic plates to develop, she would eat an ice cream cone. 4 cones into the evening, she could draw Andromeda's rotation curve by hand. The expectation was simple. Stars near the center of a galaxy, where most of the visible mass is concentrated, should orbit faster. Stars farther out, where the gravitational pull is weaker, should orbit more slowly. Just like the outer planets in our solar system move more slowly than the inner ones. When Rubin plotted the orbital speeds of stars at various distances from the center of Andromeda, she expected to see a curve that rose near the center and then fell off as distance increased. The curve did not fall. It stayed flat. Stars at the outermost edges of the galaxy were orbiting just as fast as stars near the center. This was physically impossible given the amount of visible matter. The galaxy should have been ripping itself apart, but it was not. Something unseen was holding it together. Something massive, something extending far beyond the visible disk of stars, something that did not emit light or interact with it in any obvious way. Rubin and Ford measured galaxy after galaxy, 20, 40, 60, more than 70 in total over the following decade. The rotation curves were always flat. At first, many scientists were skeptical. Some suggested it was a special case for Andromeda. Others said it only applied to certain types of galaxies. Rubin responded not with arguments, but with more data, always more data. Between 1976 and 1986, she and Ford published nearly 50 papers in their most influential work, which appeared in the June 1980 issue of the Astrophysical Journal. They presented rotation curves for 21 spiral galaxies, spanning a range of sizes and luminosities. Every single one showed the same flat curve. The evidence was overwhelming, and it was confirmed independently by radio astronomers who measured the velocities of cold hydrogen gas at even greater distances from galactic centers, finding the same flat signature. By the early 1980s, the scientific community had no choice but to accept what the data was saying. Princeton theorists Jeremiah Ostraker and Jim Peebles had run computer simulations showing that spiral galaxies would fly apart unless they were embedded in massive spherical halos of unseen matter. The observations and simulations converged on the same conclusion. Dark matter was real. It was everywhere, and it constituted at least 90% of the mass of every galaxy ever measured. Rubin was careful and humble about her discovery. She avoided the term dark matter in her early publications, preferring to let the data speak for itself. She shared credit generously with her collaborators and emphasized that science is a collective endeavor. She once wrote that still more mysteries of the universe remain hidden, and that their discovery awaits the adventurous scientists of the future. She received the National Medal of Science in 1993 and the Gold Medal of the Royal Astronomical Society in 1996, only the second woman to receive that honor in 168 years, the first being Caroline Herschel in 1828. She was frequently mentioned as a candidate for the Nobel Prize, but never received it, a fact many in the scientific community regard as a notable oversight. She died on Christmas Day 2016 at the age of 88. The massive astronomical survey telescope being built in Chile was renamed the Vera C. Rubin Observatory in her honor. Rubin's perspective on the history of the work on galaxy movements was presented in a review she gave in 2000 called 100 Years of Rotating Galaxies. In it, she wrote that it is folly to believe that we know what a galaxy is, while the extent, the density distribution, and the composition of 90% of its mass are still a dark mystery. Her own words capture both the magnitude of the discovery and the vast ocean of ignorance that it revealed. Dark matter was not a curiosity. It was the dominant form of matter in the universe. The discovery forced a fundamental rethinking of what galaxies actually are. The beautiful spirals and glowing clouds of gas that we see in telescope images are not the galaxy. They are the tip of the iceberg, the visible frosting on an invisible cake of dark matter that extends far beyond the disk of stars. Each galaxy sits within a massive, roughly spherical halo of dark matter that can be 10 or more times larger than the visible galaxy. The stars are just along for the ride, tracing out the gravitational contours of this invisible scaffolding. We now know that dark matter makes up about 27% of the total mass and energy content of the universe, compared to ordinary matter's meager 5%. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force at all. The only way we know it exists is through its gravitational influence. It bends the paths of light from distant galaxies. It speeds up the rotation of stars in galactic disks. It holds galaxy clusters together that would otherwise fly apart. And it provides the scaffolding upon which the entire large-scale structure of the universe is built. Without dark matter, there would be no galaxies. After the Big Bang, the tiny fluctuations in the density of ordinary matter were not strong enough to collapse under their own gravity and form structures. Dark matter, which interacts gravitationally, but is unaffected by the radiation pressure that keeps ordinary matter from clumping, began to collapse first. It formed a vast, invisible web of filaments and halos, and ordinary matter, drawn in by gravity, followed. Stars formed. Galaxies assembled within dark matter halos. Clusters grew at the intersections of filaments. The entire visible universe is essentially foam on the surface of a dark matter ocean, and it is dark matter, more than anything else, that determines where things go. The gravitational pull of dark matter concentrations, massive and invisible, guides the flow of galaxies across the cosmos. It is the unseen hand that is, right now, pulling our galaxy and everything around it towards something we are only just beginning to understand. The local group, our gravitational neighborhood. Before we travel to those cosmic depths, let us first look at our immediate surroundings. The Milky Way does not wander the universe alone. It is part of a small, gravitationally bound cluster of galaxies known as the local group. Picture a small town surrounded by farmland. The local group is that town. It is roughly 10 million light-years across, modest by cosmic standards, and it contains somewhere around 80 known galaxies, though most of them are small, dim dwarf galaxies that are easily overlooked. The two dominant members are the Milky Way and the Andromeda galaxy, also known as Messier 31. These two spirals contain the vast majority of the local group's mass and are, in a very real sense, the gravitational anchors of this neighborhood. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars, depending on the estimate, along with vast clouds of gas and dust. A central supermassive black hole called Sagittarius A star that weighs about 4 million solar masses, and a halo of dark matter that extends far beyond the visible disk. When you look up at the night sky from a dark location and see that pale, milky band of light stretching from horizon to horizon, you are looking into the disk of your own galaxy, edge on. The Andromeda galaxy is even bigger. It contains roughly 1 trillion stars and is about 220,000 light years across, more than double the diameter of the Milky Way. It is the most distant object visible to the unaided human eye. On a clear, dark night, it appears as a faint, fuzzy smudge in the constellation Andromeda, a tiny patch of light that contains 1 trillion suns. The photons hitting your retina when you look at it have been traveling through the vacuum of space for 2.5 million years. The light you see left Andromeda before our earliest human ancestors walked the African savanna. The third largest member of the local group is the Triangulum galaxy, or Messier 33, a smaller spiral galaxy about 2.7 million light-years away. Beyond these three, the local group is populated by dozens of dwarf galaxies, many of which orbit either the Milky Way or Andromeda like satellites. The Milky Way's most famous satellite galaxies are the Large and Small Magellanic Clouds, visible as bright patches in the southern hemisphere sky, named after the explorer Ferdinand Magellan, whose crew noted them during their circumnavigation of the globe in the early 1500s. These two irregular galaxies have been companions to the Milky Way for billions of years. The Large Magellanic Cloud, or LMC, is particularly important. Despite its modest appearance, it is a surprisingly massive galaxy, containing perhaps 10% of the Milky Way's mass. Recent studies using data from the European Space Agency's Gaia spacecraft have revealed that the LMC is on its first close approach to the Milky Way, falling inward on an elongated orbit. Its gravitational influence on the Milky Way is far greater than previously appreciated, causing our galaxy to wobble as it adjusts to the LMC's pull. In fact, the LMC is so massive that it is pulling the Milky Way toward it, rather than simply orbiting passively. Some astronomers predict that the LMC will merge with the Milky Way within the next 2 billion years, long before any encounter with Andromeda. The Small Magellanic Cloud is less massive, but equally fascinating. It is being gradually torn apart by the combined gravitational influence of the Milky Way and the LMC, leaving behind a trail of gas called the Magellanic Stream that arcs across more than 100 degrees of the southern sky. This stream of hydrogen gas is being slowly incorporated into the Milky Way, providing new fuel for star formation in our galaxy. The local group is gravitationally bound. This means that the galaxies within it are close enough and massive enough that their mutual gravitational attraction overcomes the expansion of the universe at these scales. The expansion is still happening all around us, carrying distant galaxies away. But within the local group, gravity wins. These galaxies are falling toward each other, orbiting each other, and in some cases, colliding with each other. The two most prominent satellites of the Milky Way are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as smudges of light detached from the band of the Milky Way, named after the Portuguese explorer Ferdinand Magellan, whose crew documented them during their circumnavigation of the globe in 1519. The Magellanic Clouds are irregular galaxies that orbit the Milky Way and trail behind them a vast stream of hydrogen gas called the Magellanic Stream, stretching across more than 100 degrees of the sky. For decades, astronomers assumed the clouds were long-term satellites of our galaxy, locked into stable orbits. But recent measurements using the Hubble Space Telescope suggest they may actually be on their first approach, newcomers to the Milky Way's gravitational influence that fell in from the intergalactic medium relatively recently. In cosmic terms, the Large Magellanic Cloud, with a mass roughly 1/10 that of the Milky Way, is not negligible. Its gravitational influence perturbs the orbits of stars in the Milky Way's outer halo, tugs on the trajectories of dwarf galaxies, and, as we will see shortly, may even alter the future collision course between the Milky Way and Andromeda. The Milky Way is also currently absorbing several dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, which has been torn into long streams of stars as it spirals inward. These streams, discovered in 1994 by Rodrigo Ibada, Mike Irwin, and Jerry Gilmore, wrap around the Milky Way like ribbons around a present, tracing out the path of the doomed dwarf galaxy as it is slowly digested. The Canis Major overdensity, a structure of stars near the galactic plane, may be the remnant of another galaxy that the Milky Way consumed long ago, though its exact nature remains debated. And in 2018, data from the European Space Agency's Gaia satellite revealed the ghostly remnant of a galaxy astronomers named Gaia Enceladus, a dwarf galaxy roughly the size of the small Magellanic Cloud that collided with the Milky Way some 10 billion years ago. Its stars are still identifiable, scattered throughout the inner halo on eccentric orbits, fossils of an ancient collision that helped shape the Milky Way into the galaxy we see today. Galaxy cannibalism is not unusual. It is, in fact, how galaxies grow. The Milky Way has consumed numerous smaller galaxies throughout its 13 billion year history, and the evidence of these ancient meals is written in the streams and shells of stars that thread through the galactic halo. Andromeda has done the same. At least one significant merger event in Andromeda's past, roughly 2 billion years ago, left behind telltale signs in the galaxy's structure and stellar populations. But the most dramatic event in our local group's future, the gravitational collision that has captured the public imagination for decades, is still ahead of us. The Milky Way and Andromeda are falling toward each other, and for most of the last century, astronomers believed that a head-on collision was inevitable. Collision course towards Andromeda. The Andromeda galaxy is approaching us. This is one of the most dramatic facts in all of astronomy. While nearly every other galaxy in the observable universe is receding from us due to the expansion of space, Andromeda is coming closer. Its light is blue-shifted, meaning its spectral lines are pushed toward the shorter, bluer wavelengths, the telltale signature of an object moving toward the observer. Andromeda is closing the gap between us at roughly 68 miles per second, which works out to about 250,000 miles per hour. The Milky Way and Andromeda are roughly 2.5 million light-years apart, and they are falling toward each other under the relentless pull of their combined gravitational mass. The dark matter halos surrounding both galaxies extend far beyond their visible disks. And it is these halos, each containing perhaps 1 trillion solar masses of invisible matter, that provide most of the gravitational attraction. For decades, astronomers were confident that these two galaxies were on an unavoidable collision course. In 2012, a team led by astronomer Roland van der Merel at the Space Telescope Science Institute used the Hubble Space Telescope to measure the sideways motion of stars in Andromeda, a quantity called proper motion. With unprecedented accuracy, they observed the same stars in 2002 and again in 2010. Using the positions of hundreds of distant background galaxies as fixed reference points, after painstaking analysis, averaging over thousands of stars to achieve sub-pixel accuracy, they concluded that Andromeda's sideways velocity was negligibly small. The galaxy was essentially heading straight for us. A direct collision in about 4 billion years seemed all but certain. NASA released dramatic simulations showing the event in terrifying detail. 3.75 billion years from now, Andromeda would begin to loom large in our sky, a ghostly spiral growing larger than the moon. At 4 billion years, the two galaxies would make their first close pass, tidal forces warping and stretching both spirals into grotesque shapes. At 5 billion years, the cores of the two galaxies would blaze across the sky like a pair of glowing eyes, and by 7 billion years from now, the two galaxies would fully merge into a single, bloated elliptical galaxy that astronomers have already nicknamed Milkomeda. It was a dramatic narrative, and it captured the public imagination, but science does not stand still. And in 2025, a new study threw the certainty of this collision into doubt. A team led by astronomer Till Sawala at the University of Helsinki, publishing in the journal Nature Astronomy, conducted a much more comprehensive analysis of the Milky Way Andromeda system, using updated data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft. They factored in something the 2012 study had not fully accounted for: the gravitational influence of other nearby galaxies. Specifically, they included the effects of the Triangulum galaxy, Andromeda's large satellite, and the Large Magellanic Cloud, the most massive satellite of the Milky Way. The Triangulum galaxy, it turns out, has a modest effect. Its extra mass slightly increases the probability of a merger by pulling the Milky Way more strongly toward the Andromeda system. But the Large Magellanic Cloud has a more dramatic and unexpected influence. Its orbit runs roughly perpendicular to the Milky Way Andromeda line of approach, and its gravitational tug pulls the Milky Way slightly off course, away from a direct hit with Andromeda. After running 100,000 simulations incorporating these gravitational effects and the latest observational uncertainties, Sawala's team reached a remarkable conclusion. The probability of a Milky Way Andromeda collision within the next 10 billion years is only about 50%. The chance of a head-on collision within 4 to 5 billion years the scenario NASA had so dramatically visualized dropped to approximately 2%. In just over half the simulations, the two galaxies eventually do merge, but through a much more drawn-out process. They make a close pass, their dark matter halos interact, they swing apart, gradually lose orbital energy through a process called dynamical friction, and ultimately spiral together over many billions of years. In many of the remaining simulations, the galaxies pass each other at a distance of about 500,000 light-years, 5 times the Milky Way's diameter, and continue on their separate ways, orbiting each other indefinitely without ever truly merging. In a few percent of cases, they barely interact at all. This is not to say the collision will not happen. It still might. But the certainty that characterized the earlier predictions has evaporated. As Sawala himself noted, even using the most precise observational data available, the future of the local group is uncertain. What would a collision look like if it did happen? The word collision is somewhat misleading. Galaxies are mostly empty space. The average distance between stars within a galaxy is immense. If you scaled the sun down to a ping-pong ball, the nearest star would be a P, about 680 miles away. The odds of any two individual stars colliding during a galactic merger are extraordinarily small. You could pass two galaxies through each other, hundreds of billions of stars interpenetrating, and not a single star would strike another. The distances are simply too vast, the stars too tiny relative to the spaces between them. Instead, what happens is gravitational. The tidal forces between the two galaxies would stretch and distort their shapes, pulling long streams of stars, gas, and dust into sweeping tidal tails that could extend millions of light-years. Gas clouds within the galaxies, which are far more diffuse than stars, would collide and compress, triggering enormous bursts of new star formation. Millions of new stars would ignite across both galaxies in a dazzling starburst that could light up the merged system like a cosmic bonfire. Some of these new stars would be massive, burning through their fuel in just a few million years before detonating as supernovae, scattering heavy elements through the interstellar medium and seeding future generations of stars with the raw ingredients for planets, oceans, and perhaps one day, life. The supermassive black holes at the centers of each galaxy, Sagittarius A star in the Milky Way, and its Andromeda counterpart, which is even larger, would begin a gravitational dance. They would orbit each other, gradually spiraling closer over millions of years as they transfer energy to surrounding stars, flinging those stars outward in a process called gravitational slingshot. Eventually, the two black holes would merge in a cataclysmic event that would send gravitational waves rippling through the fabric of space and time. Waves so powerful that they could be detected by instruments across the observable universe. The merged black hole would settle at the center of the new galaxy, gorging on any gas and stars unlucky enough to fall within its reach. For a time, the merged galaxy might even host an active galactic nucleus, a blazing core of light powered by infalling matter, visible across millions of light-years. Jets of superheated plasma could erupt from the poles of the black hole, shooting outward at nearly the speed of light, carving glowing tunnels through the interstellar gas of the newly formed galaxy. The merger would not happen all at once. The entire process from the first tidal interactions to the final coalescence, would take roughly 1 to 2 billion years. During that time, the two galaxies would pass through each other multiple times, each pass stripping away more gas, disrupting more orbits, and scattering more stars into the intergalactic void. Some unlucky stars would be flung entirely out of the merged system, becoming rogue stars wandering the darkness between galaxies, carrying any orbiting planets along with them into the black emptiness of intergalactic space, never to be part of a galaxy again for any observers who might be around to witness it. The night sky would be transformed beyond recognition. Imagine stepping outside on a clear night today and seeing the familiar constellations, the Big Dipper, Orion, and Cassiopeia. Now imagine those constellations slowly dissolving over millions of years as the stars are shuffled into new orbits by the gravitational turmoil of the merger. The thin band of the Milky Way would be replaced by a chaotic swirl of light. Bright knots of newly formed stars would blaze across the sky. Glowing streams of gas would stretch from horizon to horizon. And over billions of years, the merged galaxy would settle into a smooth, featureless elliptical shape, its one-sprout spiral arms gone forever, replaced by a uniform glow of aging stars. But of course, there would be no human observers. By the time any of this happens, the sun will have already entered its red giant phase, swelling to engulf Mercury and Venus, scorching the Earth to a lifeless cinder. The oceans will have boiled away. The atmosphere will have been stripped into space. Long before the galaxies meet, our planet will already be dead. And yet, as dramatic as this story is, the collision with Andromeda is only the beginning. It is a local event, a neighborhood drama. The truly grand story, the one that determines where everything in the universe is ultimately headed, plays out on a scale that dwarfs anything we have discussed so far. The cosmic web, the architecture of everything. If you could zoom out, far, far out, to the point where individual galaxies shrink to mere pinpricks of light, you would see something astonishing. Galaxies are not scattered randomly through the universe. They are organized into an intricate, interconnected network of filaments, sheets, walls, and voids that spans the entire observable cosmos. Astronomers call this the cosmic web, and it is the largest coherent structure in existence. Imagine taking a sponge, a natural sea sponge, and blowing it up to a size of billions of light years. The solid parts of the sponge, the walls and ridges, represent the filaments and sheets of the cosmic web, made of galaxies, gas, and dark matter. The holes in the sponge, the empty spaces where the sponge material is absent, represent the cosmic voids, enormous regions of near emptiness that make up most of the volume of the universe. The discovery of this structure was one of the great surprises of late 20th century astronomy. In the 1980s, large-scale galaxy surveys began mapping the three-dimensional positions of galaxies across the sky. The idea was straightforward but labor-intensive. Point a telescope at a galaxy, measure its redshift. From that redshift, calculate its distance. Do it again and again, thousands of times, and then plot all those points in 3 dimensions and see what pattern emerges. In 1986, astronomers Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics completed a slice of their CF A redshift survey and projected the results on screen. What they saw astonished them. Geller later described the moment in vivid terms. The galaxies were not scattered randomly like grains of sand tossed across a table. They traced out an intricate, foamy structure, with galaxies lining the surfaces of enormous bubble-like voids. She compared it to looking at a cross-section through a sponge, or at the suds in a kitchen sink. One of the most prominent features they discovered was a structure they called the Great Wall, a sheet of galaxies more than 500 million light-years long and 200 million light-years wide, but only about 15 million light-years thick. It was as if someone had painted galaxies onto an enormous, crumpled piece of paper. The discovery made the front page of major newspapers and fundamentally changed how astronomers thought about the distribution of matter in the universe. The cosmos was not a smooth porridge of galaxies, uniform in all directions. It had architecture. It had geometry. It had a structure on scales that nobody had predicted. Since then, increasingly ambitious surveys have filled in the picture. The Sloan Digital Sky Survey, which began in 2000, mapped the positions and distances of millions of galaxies, revealing the cosmic web in exquisite detail. The pattern is unmistakable. Galaxies cluster along filaments that can stretch for hundreds of millions of light years. Where filaments intersect, massive galaxy clusters form, dense knots of hundreds or thousands of galaxies bound together by gravity. These are the nodes of the cosmic web, the great cities of the universe, where matter has accumulated and compressed over billions of years of gravitational collapse. Between the filaments lie the voids, regions of space that are startlingly empty, containing few or no galaxies at all. Some of these voids are enormous. The Boots void, one of the largest known, stretches across roughly 330 million light-years of almost empty space. If the Milky Way were located at the center of the Boots void, we would have discovered the existence of other galaxies much later in our history, because the nearest galaxies would have been so distant that only the most powerful modern telescopes could have detected them. Galaxies would have been invisible to all but the last few decades of human technology. The voids are not truly empty, of course. They contain a thin fog of hydrogen gas, a scattering of dim, isolated galaxies, and presumably a diffuse web of dark matter. But compared to the dense filaments and clusters, they are desolate. It is estimated that voids make up roughly 80% of the volume of the universe. The glowing, galaxy-rich filaments are the exception, not the rule. We live in the minority. Most of the universe is dark and quiet and profoundly alone. And within the filaments themselves, there is a component of the universe that remained hidden for decades, the warm-hot intergalactic medium. For years, cosmologists faced an embarrassing accounting problem. When they added up all the ordinary matter they could see, the stars, the galaxies, the hot gas in galaxy clusters, the total fell short of what the Big Bang predicted should exist. Roughly 30 to 40% of the universe's ordinary matter was simply missing. Not dark matter, which was a separate puzzle, but plain old baryonic matter, the protons and neutrons that make up everything we can touch. In the early 2000s, theoretical models suggested that this missing matter might be hiding in the filaments of the cosmic web. Heated to temperatures between 100,000 and 10 million degrees. Too hot to be seen in optical light, but too cool to shine brightly in X-rays. This warm-hot intergalactic medium, or WIM, would be virtually invisible to conventional telescopes. It was not until 2020 that astronomers definitively confirmed its existence using a technique called the kinematic Sunyaev-Zeldovich effect, essentially detecting the subtle fingerprint that this hot gas leaves on the cosmic microwave background as photons pass through it. The missing matter had been found, lurking in the filaments of the cosmic web all along. Recent simulations, including the groundbreaking Millennium TNG simulation, have traced the evolution of the cosmic web from the early universe to the present day. These simulations show that the filaments are dynamic structures. They grow, stretch, merge, and sometimes fragment over cosmic time. Filaments in dense regions tend to contract and shorten as gravity pulls their contents toward the nearest cluster node. Filaments near cosmic voids, by contrast, tend to stretch and thin as the surrounding space expands. The cosmic web is not a static architecture. It is a living, breathing structure, constantly reshaping itself under the competing influences of gravity and expansion. And it is through these filaments that matter flows. Simulations reveal streams of gas and dark matter sliding along the filaments like water flowing through channels, feeding galaxies with fresh fuel for star formation. Galaxies do not grow in isolation. They are connected to their surroundings through the cosmic web, drawing sustenance from the filamentary network that links them to the broader universe. Some galaxies sit at the intersections of multiple filaments and grow enormous, gobbling up the matter that flows in from all directions. Others sit in the backwaters, far from any major filament, and remain small and dim. The cosmic web is not a random pattern. It grew from the tiniest seeds. In the first fraction of a second after the Big Bang, quantum fluctuations, those minuscule, random variations in the density of matter and energy, were stretched by the rapid expansion of space during a period called cosmic inflation. These fluctuations became the blueprint for all the structures we see today. Slightly denser regions attracted slightly more matter through gravity. Over billions of years, those overdense regions grew, pulling in gas and dark matter from the surrounding space, forming galaxies and clusters, while the underdense regions grew emptier, becoming the voids. Dark matter was the architect. Because dark matter does not interact with light, it was free to begin collapsing under its own gravity much earlier than ordinary matter, which was trapped in a hot plasma of radiation and particles for the first 380,000 years after the Big Bang. Dark matter built the skeletal framework of the cosmic web, and ordinary matter, once released from the grip of radiation, fell into the gravitational wells that dark matter had prepared. Stars formed within galaxies. Galaxies formed within dark matter halos, and halos clustered along the filaments of the web. The filaments are not just decorative, they are highways. Matter flows along them, sliding down gravitational gradients toward the densest regions. Galaxies that form within filaments are slowly funneled toward the nodes, the massive galaxy clusters that sit at the intersections. Gas streams along the filaments feed galaxies with the raw material they need to form new stars. Cosmological simulations vast computer models that simulate the evolution of millions of light years of space reproduce this web in remarkable detail. They show filaments growing, stretching, and sometimes merging as the universe ages. They show matter flowing like rivers through the cosmic landscape, always toward the densest concentrations. And it is this flow, this grand, slow, gravitational river, that carries our galaxy along with it. The Milky Way sits within a filament. It is part of the cosmic web, and the direction of its flow is determined by the distribution of mass on the largest scales imaginable. To understand where we are being carried, we need to zoom out even further, past the local group, past the Virgo cluster, to the scale of superclusters, to the most massive structures that gravitational attraction can assemble. Laniakea, our immeasurable heaven. For most of the 20th century, astronomers organized the universe into a hierarchy that went something like this. Galaxies group into clusters, clusters group into superclusters, and superclusters were the largest things around. Our own Milky Way was said to be part of the Virgo supercluster, a collection of roughly 100 galaxy groups and clusters centered on the Virgo cluster, which lies about 65 million light-years away and contains over 1,000 galaxies. The Virgo supercluster, stretching about 110 million light-years across, was considered our cosmic home. Beyond its edges, the universe was divided into other superclusters, each one a separate kingdom of galaxies. But this picture was incomplete. The boundaries between superclusters were fuzzy and arbitrary, drawn more out of convenience than any physical principle. And in 2014, an astronomer from Hawaii showed us that our cosmic home was far larger than anyone had realized. Our Brent Tully had spent decades studying the motions of galaxies. Working from the University of Hawaii's Institute for Astronomy, he and his collaborators built one of the most detailed catalogs of galaxy distances and velocities ever assembled. This catalog, called Cosmic Flows, contained thousands of measurements of what astronomers call peculiar velocities, the motions of galaxies that remain after you subtract the smooth, uniform expansion of the universe. These peculiar velocities are the fingerprints of gravity. They reveal the invisible distribution of mass in the universe, because galaxies do not just ride passively on the expanding fabric of space. They are also pulled sideways toward whatever massive concentrations of matter lie nearby. Measuring these peculiar velocities is a painstaking business. For each galaxy, you need two separate measurements: its recession velocity, which you get from its redshift, and its actual distance, which you calculate independently using methods like the Tully-Fisher relation, a technique Tully himself helped pioneer in the 1970s. The Tully-Fisher relation links the brightness of a spiral galaxy to the speed at which it rotates, giving you a distance estimate that is independent of redshift. Once you have both the distance and the recession velocity, the difference between them gives you the peculiar velocity, the galaxy's motion through space under the influence of gravity, stripped of the universe's overall expansion. Individual measurements carry uncertainties of 10 to 20%, which means that for any single galaxy, the number is fuzzy. But when you compile thousands of these measurements, as the Cosmic Flows catalog does, the large-scale patterns emerge with striking clarity. like stepping far enough back from a pointillist painting that the image suddenly snaps into focus. By mapping these peculiar velocities in 3 dimensions, Tully and his team, which included Helene Courtois of the University of Lyon, Yehuda Hoffman of the Hebrew University of Jerusalem, and Daniel Pomard of CEA Saclay, applied a sophisticated mathematical technique called Wiener filtering to the data. This algorithm smoothed over the noise in individual galaxy measurements and revealed the large-scale flow patterns, the great rivers of galaxies streaming through the cosmos. And with those rivers mapped, the team could do something remarkable. They could identify the cosmic watersheds, the dividing lines in space where the flow of galaxies splits, some falling in one direction and others falling in the opposite direction. These watersheds are the true boundaries of superclusters. Within a given supercluster, all galaxy motions are directed inward toward a common gravitational center. Between superclusters, the flows diverge, like rainwater on a mountain ridge flowing down opposite slopes into different valleys. The analogy is deliberate and illuminating. Think of the surface of the Earth with its mountain ridges and river basins. Rainwater that falls on one side of a ridge flows into one river valley. Rainwater that falls on the other side flows into a different valley. The ridge line is the watershed, the dividing boundary. Tully realized that the same principle could be applied to the cosmos. Instead of rainwater, you have galaxies. Instead of gravity pulling water downhill, you have gravity pulling galaxies toward the nearest concentration of mass. And instead of mountain ridges, you have the boundaries where the gravitational influence of one supercluster gives way to the influence of another. This was a fundamentally new way of defining superclusters. Previous definitions were based on the density of galaxies, simply looking for regions where galaxies were more tightly packed than average and drawing a boundary around them. But those boundaries were arbitrary. How do you decide where one supercluster ends and another begins when the cosmic web is a continuous, interconnected structure with no clear edges? Tully's method solved this problem by using the dynamics of the system, the actual motions of galaxies, rather than just their positions. It was elegant, physically motivated, and it produced a striking result. When Tully's team applied this method to the galaxy catalog, they found that the Virgo supercluster was not the coherent structure astronomers had assumed. It was only a small part of a much larger entity. The true extent of our home supercluster was enormous, spanning roughly 520 million light-years across, and containing the mass of approximately 100 million suns, spread across roughly 100,000 galaxies. It included the Virgo cluster, the Hydra and Centaurus clusters, the Norma cluster, and many others that had previously been classified as separate superclusters or independent structures. They needed a name for this colossal structure, and they turned to Nawa Napoleon, an associate professor of Hawaiian language at Kapiolani Community College. She suggested Laniakea, a Hawaiian word meaning immeasurable heaven. The name honors Polynesian navigators who used the stars to cross the vast Pacific Ocean, and it captures the awe-inspiring scale of the discovery. The heart of Laniakea, the point toward which all the internal galaxy flows converge, is a gravitational focal point that astronomers had been studying for decades, a region of immense mass, hidden from direct observation, exerting a pull on every galaxy within its reach. A place with a name that has captivated the public imagination since it was first coined in the 1980s. They called it the Great Attractor. The Great Attractor, the hidden gravity that pulls our galaxy. The story of the Great Attractor begins with a puzzle. In the early 1970s, astronomers began to notice something odd about the way galaxies were moving in our neighborhood of the universe. The expansion of the universe should produce a smooth, uniform recession, with galaxies drifting apart at rates proportional to their distance. But when researchers looked closely at the redshifts of nearby galaxies and compared them to their expected velocities based on the Hubble expansion alone, they found systematic deviations. Some galaxies were moving faster than expected. Others were moving more slowly. And these deviations were not random. They were coherent, as if all the galaxies in our part of the universe were being pulled in the same general direction. By the late 1970s, the cosmic microwave background provided the clearest picture yet. Satellites measuring the CMB detected a tiny but unmistakable temperature difference across the sky. A dipole. The CMB was slightly warmer in one direction and slightly cooler in the opposite direction. This dipole revealed that the Milky Way, along with the entire local group, was moving through the universe at roughly 370 miles per second, or about 1.3 million miles per hour, relative to the CMB rest frame. But relative to the CMB, you would expect no motion at all if everything were expanding uniformly. Something was pulling us. In 1987, astronomer Alan Dressler and his collaborators published a landmark paper that would change our understanding of cosmic motion. The team, which became known informally as the Seven Samurai, consisted of Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lindenbell, Roberto Turlevich, and Gary Wegner. They were an international group drawn from observatories in the United States, Britain, and South Africa. And they had spent years on a painstaking project to measure the distances and velocities of roughly 400 elliptical galaxies spread across the sky. Their original goal was to refine the expansion rate of the universe. But what they discovered, instead, was far more dramatic. A huge swath of the nearby universe, spanning hundreds of millions of light years and encompassing thousands of galaxies, was participating in a coherent bulk motion, a streaming flow that pointed unmistakably toward a single region in the southern sky. Entire galaxy clusters were being swept along, all streaming toward a point in the direction of the constellations Centaurus and Norma. The Seven Samurai gave this mysterious gravitational focus a name that captured the public imagination instantly: the Great Attractor. The name was dramatic, evocative, and perhaps a little misleading, conjuring images of a cosmic drain that was vacuuming up galaxies. The reality, as is often the case in astronomy, turned out to be both more subtle and more interesting. The Great Attractor was estimated to lie about 150 to 250 million light-years away, and the mass needed to produce the observed flow was staggering, on the order of tens of thousands of times the mass of the Milky Way. But here was the maddening part. The Great Attractor sat directly behind the plane of the Milky Way, in a region of the sky that astronomers call the zone of avoidance. Our own galaxy, with its thick disk of gas, dust, and billions of stars, was blocking our view of the very thing that was pulling us. Trying to study the Great Attractor through the zone of avoidance with optical telescopes is like trying to see a candle flame through a fog bank. The dust absorbs and scatters visible light, rendering everything behind the galactic plane effectively invisible. For years, the Great Attractor remained one of the most tantalizing mysteries in astronomy. We could feel its gravitational tug. We could measure its effects on the motions of thousands of galaxies, but we could not look at it directly. The breakthrough came from telescopes that could see through the Milky Way's dust. Infrared light and X-rays, which have longer or shorter wavelengths than visible light, can penetrate the galactic plane to varying degrees. In the late 1990s and 2000s, surveys using radio telescopes and X-ray observatories began to peer through the zone of avoidance and map the galaxies hidden behind it. The Parkes Radio Telescope in Australia detected thousands of previously unseen galaxies in the region. Its 21-centimeter hydrogen line surveys could pick up the radio emissions of neutral hydrogen gas in galaxies that were completely invisible in optical light, revealing a rich concentration of galaxies where the galactic dust had hidden them from view. X-ray surveys like the clusters in the Zone of Avoidance project mapped the hot gas within galaxy clusters, which glows in X-rays even when the individual galaxies are obscured. The 2-micron all-sky survey, or 2MASS, which mapped the entire sky in near-infrared wavelengths, provided another crucial window. Infrared light can pass through dust far more easily than visible light, and the 2MASS survey revealed the full extent of the galaxy distribution behind the Milky Way's disk for the first time, filling in a region that had been a blank spot on cosmic maps for decades. What they found was revealing, but also somewhat deflating. The mass in the Great Attractor region was significant, but it was not nearly as large as the early estimates had suggested. What they found was both revealing and disappointing. The Great Attractor was not a single, mysterious object. It was not a supermassive black hole or some exotic cosmic entity. It was a region of space containing a significant overdensity of galaxies, dominated by the Norma cluster, a rich concentration of galaxies about 220 million light-years away. The Norma cluster alone contains hundreds of galaxies, their stars and gas emitting copious amounts of X-rays as they interact with each other in the dense cluster environment surrounding the Norma cluster. A massive filamentary structure called the Norma Wall, also known as the Great Attractor Wall, stretches across the sky, adding its mass to the gravitational pull. But the X-ray surveys revealed something that forced astronomers to reassess their models. The Great Attractor was not as massive as originally estimated. A 2005 study by Dale Kosofsky and Harold Ebeling, using the clusters in the Zone of Avoidance project, found far fewer massive galaxy cluster systems near the Great Attractor than expected. The region turned out to be only about 1/10 the mass that earlier calculations had suggested. As Kosofsky himself stated, one of our goals was to uncover the true mass of the Great Attractor, and what we found is that it is not that great after all. This created a problem. If the Great Attractor was smaller than thought, it could not account for the full motion of our galaxy. The Milky Way's motion through space, measured at roughly 370 miles per second relative to the cosmic microwave background, was too fast and pointed in a direction that did not quite line up with the Great Attractor alone. Something else must be contributing. Something even bigger, even farther away. And indeed, the same X-ray surveys that revealed the Great Attractor's diminished mass also identified a significant concentration of galaxies behind it, much farther away, in the direction of the Shapley concentration. It turned out that the Great Attractor was not the final destination. It was merely a way station. A bend in the river, not the ocean, into which the river flows. The true picture that emerged was more nuanced. The Great Attractor is not a thing that is pulling us. It is a place, the gravitational center of the Laniakea supercluster, the point toward which all the internal flows converge. But Laniakea itself is in motion. The entire supercluster, all 100,000 galaxies within it, along with the Great Attractor at its heart, is being pulled toward something even more massive. Something that sits further along the line of our cosmic journey, something called the Shapley concentration. The Shapley concentration, the largest mass in our corner of the cosmos. In 1930, Harlow Shapley, the astronomer who had mapped the size and shape of the Milky Way using globular clusters a decade earlier, was conducting a survey of galaxies in the southern sky from the 24-inch Bruce telescope in Bloemfontein, South Africa. Looking toward the constellation Centaurus, he noticed something striking. An unusually rich, elongated cloud of galaxies, far denser than anything in its surroundings. He noted the observation and moved on. It would be more than half a century before astronomers understood the significance of what he had found. It took a surprisingly long time for Shapley's observation to be rediscovered. In the late 1970s, X-ray astronomers began detecting strong sources in that same region of sky. But nobody yet connected them to the galaxy cloud Shapley had noted decades before. In 1981, astronomers Jorge Melnick and Hector Quintana identified one of the major clusters in the region, calling it by its X-ray catalog designation. They noted in their paper that it sat in an area of the sky that was, in their words, extremely rich in galaxies, essentially repeating Shapley's observation from 51 years earlier, without fully realizing it. Then, in 1989, two independent groups recognized the supercluster almost simultaneously. Samak Rayshohiri, working at the University of Cambridge with automated plate measuring technology, named the structure after Harlow Shapley. Around the same time, Roberto Scaramella and colleagues spotted the same overdensity in the Abel catalog of galaxy clusters, calling it the alpha concentration. The modern name stuck. The Shapley supercluster is one of the most massive concentrations of matter in the observable universe, located roughly 650 million light-years from Earth. It is a colossal assembly of roughly 25 Abel galaxy clusters, thousands of individual galaxies, and vast reservoirs of hot intergalactic gas, all packed into a region not much larger than the Virgo supercluster, which contains only a single major cluster. At its heart lies the Shapley supercluster core, a dense chain of 3 massive Abel clusters, Able 3558, Able 3556, and Able 3562, strung together with two smaller groups in a continuous filamentary structure stretching roughly 8 megaparsecs end to end. The Able catalog lists only 5 galaxy clusters in our entire billion light-year neighborhood, with a richness class above 2, meaning they are extraordinarily dense with galaxies. 3 of those 5 are inside the Shapley supercluster. Some of them contain more galaxies than the famous Coma cluster, one of the richest clusters known to astronomy. ESA's Planck satellite, scanning the sky for the cosmic microwave background, captured images of the Shapley core that revealed the hot gas pervading these clusters, gas that shines brightly in both X-rays and at microwave wavelengths, creating a distinctive fingerprint against the afterglow of the Big Bang. The mass of the Shapley concentration is staggering. According to ESA, it boasts more than 8,000 galaxies and a total mass exceeding 10 billion solar masses, making it the most massive structure within roughly a billion light-years of our galaxy. The clusters within the Shapley concentration are not just numerous, they are violently active. X-ray observations from XMM Newton and data from Planck have revealed that the space between the core clusters glows faintly in X-rays, heated to millions of degrees by the compression of gas falling into the gravitational wells. The Shapley Supercluster Survey, a dedicated observational campaign, has mapped a 23 square degree region and found that all 11 major clusters and groups within the core lie within 1,300 kilometers per second of each other in velocity, connected by a coherent sheet of galaxies with no gaps. Velocity caustics, the telltale signatures of gravitational infall, extend right to the survey's boundary, confirming that the entire structure is gravitationally bound and actively collapsing in on itself. Galaxies within it are suffering frequent high-velocity encounters, some slamming into each other at speeds exceeding 2,000 kilometers per second. This is not a calm, quiet region of space. It is the most complex and dynamically active region in the local universe, a gravitational storm that has been raging for billions of years. When astronomers mapped the full sky distribution of galaxy clusters using X-ray surveys, they found that the Great Attractor and the Shapley concentration lie along the same general line, forming a kind of gravitational corridor. The Great Attractor, at about 220 million light-years, provides a significant nearby pull. But the Shapley concentration, at 650 million light-years, provides a much larger pull that operates on a grander scale. Think of it this way. If the Great Attractor is a whirlpool in a river that captures floating debris as it passes by, the Shapley concentration is the waterfall at the end of the river that everything is ultimately heading toward. Studies have shown that roughly half of the Milky Way's motion through space can be attributed to the Great Attractor and the local structures within Laniakea. The remaining portion, the part that the Great Attractor alone could never explain, comes from the large-scale flow toward the Shapley concentration. This means that the Great Attractor itself is in motion. It is falling toward the Shapley concentration, carrying the rest of Laniakea along with it. Recent research by Brent Tully's Cosmic Flows team has suggested that Laniakea may not even be a gravitationally independent structure. It may be a subbasin, a smaller eddy within the larger gravitational basin of attraction, centered on the Shapley concentration. If this is correct, then our cosmic address becomes even more expanded. We are not just residents of Laniakea. We are part of a structure 10 times larger, a volume that could be half the size of the largest structures ever identified in the universe. But the pull of the Shapley concentration is only half the story. In 2017, a group of researchers revealed that we are not just being pulled, we are also being pushed. The dipole repeller, the push behind our journey. In January 2017, an international team led by Yehuda Hoffman of the Hebrew University of Jerusalem, along with Daniel Pomard, R. Brent Tully, and Helene Courtois, published a paper in Nature Astronomy that transformed our understanding of why the Milky Way is moving the way it is. They had created a three-dimensional map of galaxy flows, spanning a region 1.7 billion light-years across, the most detailed map of its kind ever produced. And buried within that map was something no one had identified before. On the opposite side of the sky from the Shapley concentration, roughly 250 million light-years away, the researchers found a vast region that was almost completely devoid of galaxies. It was a cosmic void, but a special one. It was not just empty. It was actively contributing to our motion through space. They called it the dipole repeller. The name requires some unpacking. In physics, a dipole is a system with two poles. Think of a bar magnet with its north and south poles. The cosmic dipole in question is the motion of the Milky Way relative to the cosmic microwave background. That motion has a direction, and that direction is defined by two opposing influences. On one end is the Shapley concentration, pulling us forward. On the opposite end, 180 degrees away in the sky, is the dipole repeller, pushing us from behind. Two poles, one of the attractions, one of repulsion, dipole repeller. To understand how a void can push, you have to think about gravity in a slightly unusual way. Gravity is always attractive. A void, a region of nearly empty space, does not generate a repulsive force. It cannot push, but it can create a gravitational asymmetry, and that asymmetry has the same practical effect as a push. Imagine you are floating in space, surrounded on all sides by equal amounts of matter. The gravitational pull from every direction balances out, and you stay still. Now imagine that someone removes all the matter on one side of you, creating a void. Suddenly, the pull from the other side, where the matter still exists, has no counterbalance. You are pulled toward the matter, which, from your perspective, feels exactly like being pushed away from the void. The void itself is not doing anything. It is just sitting there, empty and inert. But its emptiness, the absence of gravitational attraction in that direction, is what allows the pull from the opposite direction to dominate. It is a subtle distinction, but an important one. In the language of gravity, not pulling is effectively the same as pushing. The dipole repeller sits almost exactly opposite the Shapley attractor in the sky. This means the Milky Way is being both pulled from one direction and pushed from the opposite direction. It is a cosmic tug-of-war, where both sides are cooperating to send us hurtling in the same direction. The researchers found that the repulsive contribution of the dipole repeller and the attractive contribution of the Shapley concentration are roughly comparable. In other words, the push and the pull are of similar importance at our location. What makes the dipole repeller so elusive is that voids, by their very nature, are almost invisible. You cannot point a telescope at a void and see it. There are no bright galaxies to observe, no glowing gas to measure, no X-ray sources to detect. A void announces its presence only through the effect it has on the things around it, the galaxies that flow away from it, the subtle patterns in the velocity field of the nearby universe. Identifying the dipole repeller required the research team to reconstruct the three-dimensional velocity field of thousands of galaxies, and then work backward, essentially asking the data where there must be less matter to explain the observed flows. It was like mapping a hole by watching how water flows around it. The void that constitutes the dipole repeller is located in the direction of the constellations Sculptor and Cetus, roughly 750 million light-years away. It is not the only cosmic void contributing to our motion, but it is the most significant one in the opposite direction from Shapley, which is why it creates such a clean dipole effect. Think of it this way: if you are standing on a hillside, you are pulled downhill by gravity. But if the ground behind you is also sloping away, you are effectively being pushed from behind as well. The dipole repeller is the slope behind us, and the Shapley concentration is the valley ahead. Before the discovery of the dipole repeller, astronomers had struggled to explain the full magnitude and direction of the Milky Way's motion. The pull of the Shapley concentration alone, combined with the Great Attractor, did not quite match the observed velocity and direction. The motion seemed to point slightly away from the Shapley concentration, as if some additional, unknown influence was at work. The dipole repeller resolved this discrepancy. When you add its repulsive effect to the attractive pull of the superclusters, the numbers finally match. As Hoffman stated, we found that our Milky Way galaxy is speeding away from a large, previously unidentified region of low density, as well as towards the known Shapley concentration. It has become apparent that push and pull are of comparable importance at our location. The discovery of the dipole repeller was a profound insight into the mechanics of cosmic motion. It showed that voids, the vast empty spaces that make up most of the volume of the universe, are not passive bystanders. They play an active role in shaping the flow of galaxies. The universe is not just built by the concentrations of matter that pull things together. It is also sculpted by the absence of matter that allows things to flow away. This push and pull dynamic operates at scales that are difficult to comprehend. The coherent flow of galaxies that includes the Milky Way extends across more than 1 billion light-years, roughly 1/10 of the radius of the observable universe. We are part of a river of galaxies, flowing through the cosmic web, guided simultaneously by the gravitational pull of the most massive structures in our neighborhood and the repulsive effect of the emptiest voids. And so our picture of where everything is going begins to take shape. Locally, the Milky Way may or may not collide with Andromeda, but the two galaxies, along with the rest of the local group, will eventually merge into a single large galaxy over the course of tens of billions of years. On a larger scale, the local group is being carried along with the rest of Laniakea toward the gravitational center at the Great Attractor. And the Great Attractor itself, and everything around it, is being pulled toward the Shapley concentration, while simultaneously being pushed by the dipole repeller. But even this is not the final answer. Because while gravity is pulling things together on these scales, a far more powerful force is working to tear everything apart, and it changes the fate of everything. Dark energy, the discovery that changed everything. For most of the 20th century, astronomers assumed they knew the broad outlines of the universe's future. The universe was expanding. That much had been established by Hubble in 1929. The rate of that expansion was determined by the amount of matter in the universe. Matter exerts gravitational attraction, and that attraction should slow the expansion over time, like a ball thrown upward, gradually decelerating under the pull of Earth's gravity. The big question was whether the expansion would slow enough to eventually stop and reverse, causing the universe to collapse back on itself in a big crunch, or whether it would slow but never quite stop, expanding forever at an ever-decreasing rate. To answer this question, you needed to measure how the expansion rate had changed over time. And to do that, you needed a cosmic speedometer that could work across billions of years and billions of light years. Astronomers found one in a particular type of stellar explosion called a Type 1a supernova. Type 1a supernovae occur in binary star systems when a white dwarf, the dense remnant of a dead star, accumulates enough matter from a companion star to push itself over a critical mass limit. The white dwarf detonates in a thermonuclear explosion of extraordinary violence, briefly outshining an entire galaxy. Crucially, because this detonation always occurs at roughly the same mass limit, every Type 1a supernova produces roughly the same peak brightness. They are what astronomers call standard candles. By measuring how bright a Type 1a supernova appears versus how bright it actually is, you can determine its distance, and by measuring the redshift of its host galaxy, you can determine how fast that part of the universe is expanding. In the 1990s, two rival teams set out to use Type 1a supernovae to measure the deceleration of the universe. One was the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. Perlmutter had spent years developing the techniques needed to find distant supernovae reliably. He built wide-field CCD cameras, devised ingenious observing strategies timed around the phases of the moon, and assembled a large, international team of collaborators. The other was the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University, with Adam Rees playing a key role in the data analysis. Schmidt had formed his team in 1994, using methods similar to Perlmutter's, and the two groups became fierce rivals, each racing to be the first to measure the cosmic deceleration. Both teams expected to find that the expansion was slowing down. The question was not if, but by how much. Was there enough matter in the universe to eventually halt and reverse the expansion, leading to a big crunch, or was there too little, allowing the expansion to coast forever at an ever-decreasing rate? These were the only two possibilities anyone seriously considered. Both teams found the opposite in 1998, after years of painstaking observations involving dozens of the world's most powerful telescopes, including the Hubble Space Telescope and the Keck Observatory on Mauna Kea. The two teams announced their results independently. Between them, they had studied more than 50 distant Type 1a supernovae, and every single one told the same story. The distant supernovae they had observed were dimmer than expected, not brighter, as they would be if the expansion were decelerating, but dimmer, as they would be if the supernovae were farther away than a decelerating universe would predict. The inescapable conclusion was that the expansion of the universe was not slowing down. It was speeding up. The universe was accelerating. This discovery was, by any measure, one of the most shocking and consequential in the history of science. It is not hyperbole to say that it changed everything. Every prediction about the future of the universe, every calculation about the ultimate fate of the cosmos, had to be revisited. Saul Perlmutter himself admitted that his first reaction was that of any physicist in such a situation. He wondered which part of the analysis needed recalibration. Both teams went back and checked their data, examined every possible source of error, and considered whether dust or some other effect could be fooling them. Could cosmic dust be absorbing the light of distant supernovae, making them appear dimmer? Could the supernovae themselves behave differently at great distances, introducing a systematic bias? One by one, these possibilities were tested and eliminated. The answer held. Cosmologist Joel Primack, attending one of Perlmutter's early presentations, stood up and addressed the audience directly, saying, "You may not realize this, but this is a very big problem." Other colleagues were equally stunned. Cosmologist Rocky Kalb declared at a conference in early 1998 that there must be something wrong. It is just too crazy. But the fact that two fiercely competitive teams had independently reached the same conclusion lent enormous credibility to the result. As Perlmutter later noted, one of the main reasons the community accepted the discovery so quickly was that both teams reported the same finding at almost the same time, and it was widely known that each group would have been delighted to prove the other wrong. Within months, a majority of the physics community accepted it. By the spring of 1998, at a symposium at Fermilab, about 3/4 of the physicists in the room raised their hands to indicate they believed the results were correct. Science magazine named the discovery its breakthrough of the year for 1998. Perlmutter, Schmidt, and Rees would share the 2011 Nobel Prize in Physics for their discovery. But what was driving the acceleration? Some unknown form of energy permeated the universe, exerting a kind of repulsive gravitational effect that pushed space apart. This mysterious substance was dubbed dark energy. It was not dark matter. Dark matter attracts. Dark energy repels. And unlike dark matter, which clusters around galaxies and is concentrated in specific regions, dark energy appears to be spread uniformly throughout all of space, exerting its repulsive push everywhere and always. The simplest explanation for dark energy is what physicists call a cosmological constant, the very same term that Einstein had introduced into his equations in 1917, and then abandoned. In this interpretation, dark energy is a fixed, intrinsic property of space itself. Every cubic meter of space contains a tiny amount of energy, and that energy exerts a repulsive gravitational effect as the universe expands and the density of matter decreases. The density of dark energy stays the same because new space is being created, and each new bit of space comes with its own allotment of dark energy. Over time, dark energy becomes the dominant force in the universe, overwhelming the gravitational attraction of matter and driving the expansion faster and faster. The numbers are sobering. Our best measurements indicate that roughly 68% of the total energy content of the universe is dark energy. Dark matter makes up about 27%. Ordinary matter, the stuff that makes up stars, planets, people, everything you have ever seen or touched, accounts for a mere 5%. We are a rounding error in the cosmic budget. The universe is dominated by things we cannot see, cannot touch, and barely understand. This realization is one of the most humbling in all of science. Everything that humanity has ever built, every mountain we have climbed, every ocean we have crossed, every star we have gazed upon, all of it is made of the 5%. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen in your lungs. All of these are part of the cosmic minority. The universe is, in every meaningful sense, not made for us. It is made of dark matter and dark energy, substances that our biology cannot detect and our technology can only infer. We are guests in a house built by invisible architects, and dark energy is winning on the largest scales, where gravity is too weak to overcome the cosmic expansion. Dark energy is pushing galaxies apart at an ever-increasing rate. The effect is subtle at small distances. Within galaxy clusters, within superclusters, gravity is still dominant. The expansion of space between Earth and the Andromeda galaxy, for example, is so tiny that it is completely overwhelmed by the gravitational attraction between the two galaxies. But on scales of hundreds of millions or billions of light years, dark energy reigns supreme. Galaxies beyond our gravitationally bound neighborhood are being carried away from us faster and faster. The effect compounds over time. Each second, the expansion adds a tiny bit more speed to the recession of distant galaxies. Over billions of years, these tiny additions accumulate. In the far future, if dark energy continues at its current strength, those distant galaxies will be pushed beyond the cosmological horizon. The distance at which their recession speed exceeds the speed of light, not because they are traveling faster than light through space, but because the space between them and us is stretching faster than light can traverse it. This is permitted by general relativity, which only forbids objects from moving through space faster than light. Space itself can stretch at any rate it pleases. Those galaxies will disappear from our observable universe, one by one, until the night sky contains nothing but the merged remnant of the local group, alone in an infinite, empty, expanding void. This is not a sudden vanishing. It is a slow fade. Over the course of roughly 150 billion years, the galaxies beyond our local gravitational neighborhood will gradually dim as their light is redshifted to longer and longer wavelengths by the expansion. Eventually, their light will be stretched beyond the infrared, beyond radio waves, to wavelengths so long that no conceivable instrument could detect them. they will still exist. They will still contain stars, planets, perhaps even civilizations. But they will be forever beyond our reach, as surely as if they had never existed at all. But that prediction depends on a critical assumption: that dark energy is constant, that it does not change with time. And very recent evidence suggests that assumption might be wrong. The Daisy revolution. Cracks in the cosmic constant. In March 2025, the Dark Energy Spectroscopic Instrument, known as Daisy, released its most detailed analysis of dark energy to date. The results sent tremors through the physics community. Daisy is an extraordinary machine. Mounted on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona, it is designed to simultaneously capture the spectra of 5,000 galaxies at once. Using an array of 5,000 tiny robotic fiber positioners that can each be aimed at a different celestial target with a precision of 1/10 the width of a human hair. Over its first 3 years of operation, it had measured the positions and velocities of nearly 15 million galaxies and quasars, building the largest three-dimensional map of the universe ever created. This map spans 11 billion years of cosmic history, reaching deep enough into the past to trace the evolution of the universe from its matter-dominated era to the present day of dark energy dominance. To appreciate the scale of what Daisy has accomplished, consider that the entire Sloan Digital Sky Survey, which ran for over a decade and revolutionized our understanding of the cosmic web, measured roughly 1 million galaxy spectra. Daisy has measured 15 times that number in just 3 years, and it is still going. By the time the project ends, it aims to have measured roughly 50 million galaxies and quasars, building a 3D map of the universe so detailed that it will allow cosmologists to trace the expansion history with a precision that was previously unimaginable. Daisy's primary tool is a feature called baryon acoustic oscillations, or BAO. To understand what these are, you need to rewind to the very early universe, roughly 380,000 years after the Big Bang, when the cosmos was a screaming hot fog of hydrogen plasma, photons, and dark matter. In that primordial soup, gravity would pull matter together into clumps, but the resulting pressure from photons pushing outward would resist the compression. The tug-of-war between gravity pulling inward and radiation pushing outward created waves, actual sound waves, rippling through the plasma at roughly half the speed of light. When the universe finally cooled enough for neutral atoms to form, and the fog cleared, those sound waves froze in place, imprinted on the distribution of matter as a subtle preference for galaxies to be separated by a specific distance, roughly 490 million light-years in today's expanded universe. That preferred distance is the BAO scale, and it acts as a cosmic standard ruler. Imagine finding a ruler baked into the fabric of reality itself, one whose physical size you know with high precision. By measuring the apparent size of this ruler at different distances, and therefore at different epochs of cosmic history, you can track exactly how the universe has expanded over time. It is like watching a loaf of bread rise in an oven. If you embedded raisins at fixed distances apart in the dough before baking, you could track the expansion of the bread by measuring how far apart the raisins end up at different stages. BAO does the same thing for the universe. And from that expansion history, you can infer the behavior of dark energy, because the expansion rate is determined by the balance between matter's gravitational attraction and dark energy's repulsive push. If dark energy is a cosmological constant, as the standard model of cosmology assumes, then its effect on the expansion rate should follow a very specific, predictable pattern. The DAISY data, taken alone, are consistent with this standard model. But when the DAISY measurements are combined with other observations, including data from the cosmic microwave background and from supernova surveys, something interesting happens. The data fits slightly better if dark energy is not constant. If, instead of being a fixed property of space, dark energy's strength changes over time. Specifically, the combined data suggest that dark energy may have been stronger in the past and is gradually weakening. The statistical significance of this preference, measured in terms of standard deviations or sigma values, ranges from about 2.8 sigma to 4.2 sigma, depending on which combination of datasets is used. In physics, a 5 sigma result is the gold standard for a discovery. The DAISY results are not there yet, but they are getting close. If dark energy is weakening over time, the implications are staggering. The entire future of the universe depends on what dark energy does. If it is constant, we get the big freeze, an eternal, cold, empty expansion. If it strengthens over time, we could face a big rip, where the accelerating expansion eventually becomes so violent that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms, and finally the fabric of space-time itself. But if dark energy is weakening, as the DAISY data hints, something very different could happen. If dark energy weakens enough, it could cease to dominate the universe. The expansion could slow down, and in the most dramatic scenario, if dark energy not only weakens, but reverses sign, becoming attractive rather than repulsive, the universe could stop expanding and begin to contract, heading toward a big crunch, a reversal of the Big Bang in which all of space, time, and matter collapses back to a single point. As Durham University professor Carlos Frank told the press when the DAISY results were first released in 2024. If these hints are confirmed, our earlier understanding goes out the window. And essentially, we have to start from scratch. That means revising our understanding of basic physics, our understanding of the Big Bang itself, and our understanding of the long-range forecast for the universe. It is important to emphasize the uncertainty here. The DAISY results are tantalizing, but not conclusive. The collaboration itself cautions that more data is needed. DAISY is currently in its 4th year of observations and aims to measure roughly 50 million galaxies and quasars before the project ends. Each additional year of data will sharpen the picture. Other experiments, including the European Space Agency's Euclid mission and the Vera C. Rubin Observatory in Chile, will provide independent measurements that can confirm or challenge DAISY's findings. But even the possibility that dark energy might be changing has injected a sense of excitement and a healthy dose of anxiety into cosmology. For 25 years, the standard model of cosmology, lambda CDM, has been remarkably successful at explaining the universe. It accounts for the cosmic microwave background, the distribution of galaxies, the relative abundances of elements, and the accelerating expansion. If dark energy turns out to be dynamic rather than constant, then the foundational equation of modern cosmology will need to be revised, and with it, every prediction we have made about the future of the universe. The final destination, where is everything going? And so we arrive at the ultimate question. Given everything we have learned about the local motions of galaxies, the pull of the Great Attractor, the flow toward the Shapley concentration, the push of the dipole repeller, and the mysterious behavior of dark energy, where is everything in the universe going? The answer has two parts, and they exist in tension with each other. On the scale of our immediate cosmic neighborhood, gravity is pulling things together. The Milky Way and Andromeda, regardless of whether they collide in 5 billion years or continue orbiting for much longer, will eventually merge. The rest of the local group will follow. Over hundreds of billions of years, all the gravitationally bound galaxies in our vicinity will coalesce into a single, enormous elliptical galaxy. Beyond that, the flow toward the Great Attractor and the Shapley concentration will continue, drawing more and more of the surrounding matter toward these gravitational centers. Galaxy clusters will merge into superclusters. Superclusters will combine into even larger structures. Gravity never stops trying to assemble things, but here is the cruel irony. Dark energy will prevent gravity from finishing the job. Even as gravity draws nearby galaxies together, dark energy is accelerating the expansion of space on the largest scales. The Laniakea supercluster, for all its grandeur, is not gravitationally bound. The galaxies within it are not orbiting a common center in the way that stars orbit the center of a galaxy. The flows toward the Great Attractor are real, but they are temporary. They exist because dark energy has not yet completely overwhelmed gravity at these scales, but it will. Given enough time, the accelerating expansion will stretch the cosmic web apart. The filaments will thin, the flow will slow, the superclusters will disperse. What remains will be determined by what is gravitationally bound. Only structures that are compact enough and massive enough to resist the expansion of space will persist. Galaxy clusters, the dense nodes of the cosmic web, are gravitationally bound and will survive as individual entities. The merged local group galaxy, the remnant of the Milky Way and Andromeda, will survive, but it will be alone. Over the course of roughly 150 billion years, every galaxy outside of our local gravitationally bound supercluster will be carried beyond the cosmological horizon by the expansion of space. One by one, the lights will go out. Not because the galaxies are being destroyed, but because they are being removed from our observable universe. Imagine standing on a beach, watching ships sail toward the horizon. One by one, they disappear below the curve of the Earth. They are not gone. They are just beyond the line of sight. The galaxies will disappear in much the same way, carried beyond the horizon of the observable universe by the expansion of space. A civilization living in that far future, billions of years from now, would look out at the night sky and see only its own merged galaxy. Every other galaxy would be gone. They would have no evidence that the universe was ever anything other than a single island of stars surrounded by infinite darkness. They would not know about the Big Bang. They would not know about the cosmic microwave background because it too will have been stretched to undetectable wavelengths. They would not know about dark energy, because without distant galaxies to observe, they would have no way to measure the expansion. They would live in a universe that appears static, eternal, and lonely, with no way to know that it was ever otherwise. It is a strange and melancholy thought. We live in a cosmological window, a brief epoch when the universe is old enough for intelligent life to have evolved, but young enough that the evidence of its history is still visible. The cosmic microwave background is still detectable. Distant galaxies are still within sight. The expansion is measurable. We can reconstruct the story of the universe because the clues have not yet been erased, but they will be. Now let us extend the timeline even further into what physicists call the degenerate era and beyond. Because the heat death of the universe is not a sudden event. It is a slow, grinding, unfathomably long process of decay in about 1 to 100 trillion years from now, depending on the rate of star formation. The last stars in the universe will burn through their fuel and go dark. The most common stars in the universe, red dwarfs, are also the longest lived, sipping their hydrogen fuel with extraordinary frugality. A red dwarf born today could continue shining for 10 trillion years or more, far longer than the current age of the universe. But even these miserly stars will eventually exhaust their fuel. When the last red dwarf flickers out, the era of starlight will end. No new stars will form, because the gas needed to make them will have been used up, locked away in stellar remnants, or dispersed too thinly across space to collapse. The universe will grow steadily darker, lit only by the fading embers of dead stars. White dwarfs, the dense remnants of sun-like stars, will slowly cool over trillions of years, fading from white to yellow, to red, to infrared, to invisible. They will become what astronomers call black dwarfs, cold, dark spheres of carbon and oxygen floating silently through a universe of perpetual night. No black dwarf has ever existed yet, because the universe is not old enough for any white dwarf to have cooled to that state. But given sufficient time, trillions upon trillions of years, every white dwarf in the universe will go dark. Neutron stars, the superdense remnants of more massive stars, will also cool and fade. Their intense magnetic fields will gradually weaken. Their rapid spins will slow. Over inconceivable timescales, they too will become dark, inert objects, cold and forgotten. Black holes will become the dominant objects in the universe. Stellar mass, black holes, born from the collapse of massive stars, will persist for unimaginable stretches of time. Supermassive black holes, formed from the mergers of galaxies, will grow to even greater sizes as they occasionally swallow the rare stray object that wanders too close. In the merged remnant of the Milky Way and Andromeda, the central black hole could reach tens of billions of solar masses, a leviathan sitting at the heart of a dead galaxy. But even black holes are not eternal. Stephen Hawking showed in the 1970s that black holes slowly radiate energy through a quantum mechanical process now called Hawking radiation. At the edge of a black hole's event horizon, quantum fluctuations constantly create pairs of virtual particles. Normally, these particles annihilate each other almost instantly. But near the event horizon, one particle can fall into the black hole while the other escapes. From the outside, It looks as if the black hole is emitting radiation and slowly losing mass. The process is extraordinarily slow. A black hole with the mass of our sun would take about 10 to the power of 67 years to evaporate, a number so large that writing it out would require 67 zeros after the one. A supermassive black hole with 1 billion solar masses would take on the order of 10 to the power of 100 years or more. To put this in perspective, the current age of the universe, 13.8 billion years, is utterly insignificant compared to these timescales. If the age of the universe were a single second on a clock, the evaporation time of a supermassive black hole would be longer than the age of the universe, multiplied by itself billions of times over. But given enough time, even these titans will evaporate. The last black hole will emit its final photon, and the universe will enter what physicists call the dark era. All that will remain is a thin, diffuse gas of photons, neutrinos, electrons, and positrons, spread across a space so vast and so cold that nothing interesting can happen. The temperature of the universe will approach, but never quite reach absolute zero. The universe will have reached maximum entropy, the state of ultimate disorder, where no energy gradients exist to drive any physical process. No structure can form. No work can be done. No life can exist. This is the heat death of the universe. It is the most widely accepted prediction for the ultimate fate of the cosmos, assuming that dark energy is a cosmological constant, and that the laws of physics, as we understand them, hold true indefinitely. But as we discussed, the DAISY results suggest that dark energy might not be constant. And if dark energy changes over time, the future could look very different. If dark energy strengthens, becoming what physicists call phantom dark energy, the expansion of the universe would accelerate more and more rapidly. The Big Rip scenario, first described by Robert Caldwell of Dartmouth College, would play out on a definite timetable. About 200 million years before the end, galaxy clusters would be torn apart. About 60 million years ago, individual galaxies would be shredded. Months before the end, solar systems would disintegrate. Minutes before, planets would explode. And in the final fraction of a second, atoms themselves would be ripped apart, followed by the rupture of the fabric of space-time. Some calculations place this event roughly 22 billion years in the future, though the exact timing depends on parameters we do not yet know. If, on the other hand, dark energy weakens or vanishes entirely, the universe's expansion could slow and eventually stop. If dark energy reverses signs, the universe could begin to contract, growing denser and hotter as space collapses. The endpoint would be a big crunch, a singularity of infinite density, the mirror image of the Big Bang. Some physicists have speculated that a big crunch could give rise to a new Big Bang, creating a new universe in an endless cycle of expansion and contraction, a model called the Big Bounce. And then there are the truly exotic possibilities. Vacuum decay, for instance. Our universe might exist in a metastable state, a kind of false vacuum where the energy of empty space is not at its lowest possible value. Think of a ball resting in a shallow dip on the side of a mountain. It looks stable. It sits there comfortably, but it is not at the bottom. The true lowest point, the deepest valley, lies below, a sufficiently strong nudge could send the ball rolling over the edge and tumbling down to the true minimum. In the case of the universe, that nudge would be a quantum fluctuation, a random fluctuation that could occur anywhere in space at any time. If such a fluctuation were to nudge a tiny region of space into a lower energy state, the true vacuum, a bubble of new physics would form. The boundary of this bubble would expand outward at the speed of light, and within it, the fundamental constants of nature, the masses of particles, the strengths of forces, everything we know about physics, could be completely different. Matter as we know it would cease to exist. Atoms would be impossible. Stars, planets, life, all of it would be incompatible with the new rules. The bubble wall would be undetectable until it arrived, because it travels at the speed of light, and no signal can outrun it. There would be no warning, no time to prepare. One moment, the universe works as we expect. The next, it does not. This could happen at any moment, or it might never happen at all. Calculations involving the Higgs boson mass suggest the universe may indeed be metastable, though the timescales involved, if decay occurs, stretch far beyond any number with practical meaning, potentially exceeding 10 to the power of 100 years or more. We do not know which of these fates awaits the universe. And that is perhaps the most honest and most humbling thing we can say. For all our extraordinary progress, for all the centuries of observation and theory and discovery that have brought us from a world where the Milky Way was the entire universe to a world where we can map the cosmic web across billions of light years. The ultimate fate of everything remains uncertain. We are still peering through the fog, still tracing the rivers of gravity, still listening to the faint whisper of the cosmic microwave background, trying to make out the shape of what lies ahead. There is something deeply human about this quest. Every civilization in history has looked up at the night sky and asked where it all is going. The ancient Egyptians imagined the sky as a goddess whose body arched over the earth. The Norse imagined a great serpent that encircled the world, waiting for the final battle of Ragnarok. The Hindu tradition speaks of cycles of creation and destruction that repeat for all eternity. In every case, the question is the same. Does the universe have a destination? Does the story have an ending? Modern cosmology has given us the most detailed, most rigorously tested answers to these questions that humans have ever possessed. And yet, in a poetic twist, those answers are more uncertain now than they were just a few years ago. The DAISY results are only one crack in the foundation. Another, perhaps even more troubling, is what cosmologists call the Hubble tension. When scientists measure the current expansion rate of the universe using the cosmic microwave background and project forward, using the standard lambda CDM model, they get a value of about 67.4 kilometers per second per megaparsec. But when they measure the expansion rate directly, using nearby standard candles like Cepheid variables and type 1a supernovae, they get a higher value, roughly 73 kilometers per second per megaparsec. The discrepancy is small in absolute terms, but statistically significant, now exceeding 5 sigma, the threshold that in physics normally constitutes a discovery. Something is wrong. Either there is a subtle systematic error in one or both measurement methods that has eluded years of scrutiny, by the best observational astronomers in the world. Or the standard model of cosmology is incomplete. Some new physics, something not accounted for in our current equations, must be at play. Proposals range from additional species of neutrinos to exotic forms of early dark energy to modifications of general relativity itself. No consensus has emerged. The Hubble tension, combined with the Dacey results and the ongoing debates about the nature of dark energy, all suggest that our best model of the universe, lambda CDM, may not be the final word. Something deeper, something stranger may be going on. But here is what we do know. Right now, at this very moment, you are moving. Your planet is spinning. Your star is orbiting. Your galaxy is falling toward Andromeda, being pulled toward the Great Attractor, flowing with the rivers of Laniakea toward the Shapley concentration, and being pushed from behind by the dipole repeller. You are part of the largest coherent motion in the observable universe, a cosmic river of galaxies stretching across 1 billion light years, flowing toward a destination that we are only now beginning to map. And above all of this, woven through the fabric of space itself, dark energy is stretching the universe apart, gently at first, but with gathering strength. Gravity assembles. Dark energy disperses. The two forces have been locked in this ancient contest since the beginning of time, and the outcome is still being decided. We sit at a remarkable intersection. We are large enough to think, but small enough to wonder. We are old enough to understand, but young enough to still be surprised. We live in a universe that is simultaneously coming together and flying apart, building and destroying, creating pockets of warmth and light in an ocean of cold and dark. And we are, as far as we can tell, the only beings in the known cosmos who have ever looked up at the sky and asked, "Where is all of this going?" The galaxies will not answer. The stars will not explain. The dark matter will continue its silent work, shaping the cosmos with a hand we cannot see. And dark energy, that mysterious, pervasive, inexorable force, will continue to stretch the universe toward whatever fate awaits it. A fate that even now, after centuries of looking up, we are only beginning to glimpse. But consider this. Of all the things the universe has produced, from quarks to quasars, from neutrinos to neutron stars, from the hot plasma of the Big Bang to the cold dust of dying galaxies, the most extraordinary thing it has created is the capacity to ask questions about itself. A universe without observers is a universe that simply is, expanding and contracting, assembling and dispersing, with no awareness of its own grandeur or tragedy. But we are here, and because we are here, the universe can look at itself and wonder. Every great discovery in this story, from Slipher's redshifts to Hubble's expanding cosmos, from Zwicky's intuition about missing mass to Rubin's flat rotation curves, from the shocking acceleration of the expansion to the Dacey hints that dark energy may be evolving. Every one of these was made by a human being standing on a small rock, orbiting an average star in the suburbs of an unremarkable galaxy, looking outward and asking, "What is going on out there?" And every answer, no matter how complete it seemed at the time, eventually opened the door to a deeper, stranger, more beautiful question. That is where everything in the universe is going, not just toward the Great Attractor, or the Shapley concentration, or the heat death, or the Big Rip. The universe is going toward the next question. And we, fragile and temporary as we are, get to be the ones who ask it. The journey continues. The rivers of gravity flow on, and the universe, in all its beauty and terror, is still deciding where it wants to go. If you enjoyed this journey through the cosmos, please like and subscribe, and leave a comment below to let us know what you think. Thanks for watching, and we will see you next time.